Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome the many people binge watching all the lectures before the exam. So today we are going to look at a completely different data shape. We slightly started last time, which are data cubes. I told you there are fundamental shapes of data, basically tables, cubes, graphs, trees, and text, aka vectors. And today we are focusing on the data cube. So what I want you to see here is that we have the same principles as for tables of data independence, meaning that we have a logical data model. We will have a query language and so on and so on. So it's just a different paradigm. But the idea of a database management system is exactly the same. So as a reminder of what I told you last time, the most important slide to remember is that OLTP, which is the good old 1970s way of doing databases to basically run your day-to-day business, is OLTP, online transaction processing, and it has a lot of rights. And that's because your customers purchase products, register to your website, your inventory changes, and so on. So that's the day-to-day business, lots of rights. In OLAP, this is when you sit back and focus on the quarterly reports or all the fancy reports. So here you just want to read the data. You're not interested in modifying anything. You just want to read and analyze the data. And so that means that the way you are going to design your database system is completely different from the OLTP case, because if you only need to read data, there's a lot of problems you no longer have, such as the update anomalies, delete anomalies, and so on that you have in the normal forms. So again, to continue to contrast the two, in OLTP, remember, it's the day-to-day business. It's people searching specific products on your website. It's you looking up a specific customer. So you're looking at very specific portions of your table. These are the highly filtering queries that we discussed and that can be made very fast with indices. And then in OLAP, it's the opposite. You want to analyze data like the whole database, the whole company. So you want to join over the whole thing to compute your quarterly sales and how much did you sell in every country of the world. So it's going to take a lot of time because these queries are going to join all the tables in order to aggregate all of that. So this is a completely different paradigm. Then it also makes a difference in terms of time, because we saw that in OLTP, these highly filtering queries, you can use hash indices, tree indices that we covered last week and the week before. And this is very fast. You get an answer within a few milliseconds, right? If your query is highly filtering, super, super fast. The people on the website don't even notice anything, right? But in the case of OLAP, it's different. It's what we call slow interactive. So typically, what people can do is sit in front of a spreadsheet software like Excel, connect to some OLAP system, some OLAP database, and then they are going to manipulate cubes. But this takes time. So whenever they modify something, it's not going to just take a few milliseconds. It can take a few seconds, a few minutes, and the even longer term running queries can even take hours or days, right, when you analyze at these levels. So we are really not talking about this instant response that you need for your web shop on the OLTP side. So I told you that because in OLTP we have a lot of writes and on OLAP we have a lot of reads, that actually makes a difference, because in OLTP, we want consistency. Why do we focus on that? Because the data keeps getting modified. And you want to make sure that as you modify your data, it remains consistent. For example, your inventories should always be positive, that kind of things, right? If you start in the negative, it's a trivial example, but maybe not exactly like that in real life. But basically, you want to make sure that you keep your consistency constraints at all times when you update the data. But if you are in OLAP, you don't actually update any data. So you don't care. If the data is consistent at the beginning, the data doesn't change. So it will still be consistent when you query it, right? So in OLAP, we actually don't care about redundancy. We actually love redundancy. And so that means that what I told you with the problems that drove to the normal forms, the fact that you have update anomalies, delete anomalies, and so on, we don't care about them. Remember that these anomalies came from the fact that we put everything in the same table, that is in the first normal form, but not more. that leads to a lot of replication. There's a lot of duplicate values in this table. And these duplicate values come from the functional dependencies, right? Because you have the same value in a column, it leads to the same value in another column. So there's a lot of redundancy. And in OLAP, we don't mind. So in fact, in OLAP, we don't even bother going to the high normal forms. We can absolutely live with even just the first normal form. It's totally fine. For whom is that clear? Yes, okay. And then I have these slides that you can look at it offline, but basically it's a summary of some more of the differences that you basically get between OLTP and OLAP. So some of them I already said, like the speed, the space, the freshness, for example. In OLTP, you want serializability. This is what I explained about the transactions and Alice and Bob and the fact that they should feel like they are the only ones using the database. In OLAP, you don't care. The data never gets modified. What you care about, however, is reproducibility. If you produce a fancy report for the C-level executives of the company, you want to be able to reproduce it if people ask back about the origin of the data. So this is a different focus, right? So in the design, for example, in OLTP, we love many normalized tables, second, third, Boyce code normal form. And in OLAP, we can denormalize a little bit and get back to these big tables that do many things and that are in a lower normal form. Okay, but this is just a high-level introduction. And in fact, what I like to do now is start getting more into the details of OLAP. So I will first tell you on OLAP itself, on some features of it, and then I will dive into the data model of OLAP, just like we did for tables with rows and columns, or you know that a table is a set of tuples or a set of records. I'll show you what a cube is. Every time I walk in the lecture hall, and then I get too far, and when I click, it doesn't work anymore. So I have to get back. So what characterizes OLAP and data cubes in general is motivated on where it all started in the 1990s. It started with specific use cases, very specific use cases. It's basically analytics on your customers and products. It can be census data. In fact, that's probably the oldest use case ever. Like IBM, for example, was created like this, I think even at the end of the 19th century, very long ago. And web analytics, for example, you have all the logs of your websites that you want to analyze, scientific data, and so on and so on. So it's really specifically focused use cases, and that means that the products that the companies came up with target specifically these use cases, right? They really have this in mind when they conceive the products. One consequence is that for all these use cases, time actually matters. So we really want to look at the data, not just like the way it is today. In OLTP, you're interested in today, right? You want your inventory right now, you want your orders right now, you want the customers on your website right now. But in OLAP, you like to navigate back in time. Why? Because I don't know who already see a quarterly report of a company in Switzerland, in the US, balance sheets, income statements. Okay, some of you. So if you look at these reports, they will have the data of the fiscal year that they are reported about, but they also have the previous fiscal year, right? Or the previous quarter, or the previous fiscal year. And you see the balance sheets next to each other. And so in OLAP, we really love to go back in the past, typically all the way to 10 years ago. More than 10 years ago is a bit less common. There are various reasons for that. Sometimes it's just that the data is too old, it has changed too much, so it would be too much of an effort to do it. Even though I remember that was actually continuing education participants who shared a bit of experience from their company, and some said that they actually once went so far back in the past that it was actually on paper, and they had to look at the plans of the water pipes in the building. That sort of very, very old stuff that they wanted to analyze. Okay, so we love to get back in the past, and that means that time is a very important dimension. We really want this to be part of what we display in a cube. We see that's the dimension of a cube. Another aspect is what we call non-volatility. It really again, is about the fact that we don't update the data. So what you do is you load your data into the system, into your OLAP. It's a data warehouse, that's often called. And then you access it and build your reports, period. It's frozen. You don't modify it. The data is like this, and that's it. Right? There is no updates, deletes, or whatever. The third aspect is that it is integrated in the whole company ecosystem. A company has a lot of different databases and database systems and moving parts. For example, customer relationship management, ERP, I think it's enterprise resource planning, if I'm correct, OLTP databases, so that's PostgreSQL, maybe even some files that could be on data lakes, I don't know. That is the day-to-day data, right? So this is, they manage the customers, they manage the inventories and so on. They have all of their data in there. These are the systems that basically run on a day-to-day basis and that have to run efficiently and in real time. So when you want to run your reports, create your reports, and manipulate your data cubes, you first need to create them. And so what that means is that you need to take all of the data that is in there and import it into your system, into what's called materialized views, right? You need to basically create your data cubes in there, right? And once in a while, basically, I don't know, depends on the company, but maybe every day, every week, every month, you just import the new data and add it to the data warehouse right here, right? And then once you have all the cubes in the data warehouse, then you can analyze it, you can build your reports, you can even mine, use machine learning or whatever you want to create them. But here's the thing. You might think, it's an easy task. All you need to do is log to the database and put your regular imports, to basically bring the data in there. But the thing is, if you actually would go ahead and do it without any further thinking, you're going to end up with a lot of angry people knocking at your door. Like, what on earth are you doing? Why? Because if you massively import a lot of data from all of these systems, this is going to slow down everything. Might even take down the website. So this is a problem, and you cannot just import the data at any time just like that. So typically, these are things you schedule. You schedule them carefully, typically during the night, when the system is not actually really active. So you have to be careful about this. And this is also the reason why you pour the data into a separate system. Because for exactly the reason I told you, you cannot just directly query the data in these systems. For the same reasons, these are massively joining and aggregating queries. This is going to slow down everything, right? So you really need to carefully schedule importing the data in the night when nobody's using the systems into a separate system that's called the data warehouse. And then in the data warehouse, you analyze it, and then you're fine because you're the only one using the data warehouse. For whom is that clear? Right, on the high level. So this is how it concretely works in a company. Now there is this little word in the middle that is actually made of 3 letters, ETL, but we love to create words in English, so ETL has even become a verb. Who knows what ETL means? Who never heard ETL? Okay. So ETL means extract, transform, load. This is actually the process of importing your data. And basically what you have to do is extract, so it means you take it from the database. You need to extract from the logs of Apache, from maybe you have to set up gateways between the actual databases and your warehouse to automatize it. And you might have triggers, right? That when something happens, then it triggers transferring some data over. So this is extract. Extract also means selecting what you want to import. You don't want to import everything, right? So it might involve some selection queries that specifically import specific database, specific data, specific records, right? Once you have extracted it, you need to transform it. What does it mean to transform? It means that you might need to modify the data. You have to basically organize it as a cube, so it requires a bit of transformations in there. You need to clean up the data, like completely trivial things like hair to Mr. and so on, to basically harmonize and make everything consistent in terms of languages, in terms of data formats. Maybe the dates formats are not all the same and so on. So a lot of value transformations that you need to carry out in there. In fact, this can go into the $1 million when you typically hire these big consulting companies for data migration. You know, that's really there's a lot of money involved in there and a lot of business just to do that, because it seems trivial, but it is very, very difficult to actually orchestrate in a way that doesn't break anything. And then you load. Loading means that you have transformed everything, and now you pour it into the data cubes, right? So you might have some integrity constraints, just like the same we have in PostgreSQL for the tables, you know, null, not null, unique, and so on. Then you might build indices, just like in PostgreSQL, we have 3 indices, hash indices, and so on. We can also have indices for our data cubes. You might partition it if it's too much for a single machine. This is what we call in big data for engineers. You can spread it in a cluster and so on. Now, while I mentioned this in the context of data cubes, this isn't specific to data cubes. ETL can be done for any data in and out, right? You can do it from table to table, from table to trees. You can do it from reading files from the internet to pouring them into a document store or PostgreSQL. This is very, very generic. And so instead of saying extract, transform, load, we just say ETL. And ETL is even a verb. You literally say that you ETL your data over to the data warehouse, right? So don't be surprised if you actually see that word at other places used as a verb. Now, because these are very specific use cases and these are use cases that are actually extremely useful, what happened is that first startups were created. One of them is called Essbase, Cognos, and so on. So these were startups back then that started building these systems. And then what happens is very interesting, is that the top 3 database vendors, commercial is basically Microsoft, IBM, and Oracle, each bought their startups, or at least Oracle bought Essbase, IBM bought Cognos. Microsoft, I'm not sure if it's actually bought or did it themselves, I can't remember, but this is what they call analysis services. And the reason for this, as we will shortly see, is that these data cubes can actually be implemented very nicely on top of relational database systems, on top of tables. So this is the reason why these table makers, so these relational database systems companies, actually swallowed in some consolidation events these companies that were dealing with data cubes, right? And then there is a 4th player, even though it didn't come from a relational database company, that is SAP, right? HANA. So these are the top 4 players. Of course, there's others, but just to give you an impression of the landscape. Now, if you look between the systems, overall, the principles are the same. I'm going to basically cover that today. But you might have, of course, a few differences in cosmetics, in languages, in modeling. So it's not exactly the same. But of course, if you have learned one, then you can easily learn the other. Okay? So now we are getting to the meat, to the logical part of the data model of data cubes, so that data cubes have no more secrets for you. And then we'll see how we will actually hit them with a hammer until they fit in a table. So that's the model. Remember that a table has rows and columns. So it's 2-dimensional, a table, right? But a cube is multidimensional. On this screen, I gave an example of 3 dimensions because we human beings are able to perceive 3 dimensions. They can have more. They can have 4, 5, 10 dimensions, right? Who studied linear algebra? Okay, so all of you understand that you can have a lot of dimensions beyond 3, and everybody else, so just that you know it, that we can actually totally mathematically make it work with more dimensions than 3. There's a few tricks, of course, for understanding it as humans. So with this example, with 3 dimensions, this is a cube. 1 dimension is, I told you about the time, this time-oriented use cases. So we have maybe the last year, the previous year, the year before, the year before. Then here we have the products. Maybe these are the TV sales, the phone sales, the server sales, the smartwatch sales, and so on and so on. And then we have the countries of sale. So let's say this is in DACH, so Deutschland, Österreich, Schweiz, and that's Germany, this is Austria, no, sorry, this is Switzerland, I put it there, Switzerland, Austria, and Germany, right? And what happens is that for every combination of these three, for a specific year, let's say the year 2022, for a specific product, let's say the server, and for a specific country, that locates a cell in here in which there is a number. That number here is 7, and it corresponds to basically that layer here that says that's the year 22. Maybe this is 23, 22, 21, 20. So this is 22. This layer right here corresponds to the servers, maybe smart switches and so on. And then the front layer corresponds to Switzerland. So who sees that the intersection of the three gives you that small cell? You see that? Okay. So this is exactly how it works. The dimensions give you the context that you have here, 2022 in Switzerland, the servers that were sold there. And here we see there are 7 of them. And every little cell in here also has its own value. So you have a value for smartwatches sold in Austria in the year 2021 in a different cell and so on. So far, so good? Okay. So this is the first part of the data model, right? That you have these cubes. Now, what do we have as dimensions? So there can be more than 3. Some dimensions are actually quite typical in the systems that you almost always see that kind of dimension. One dimension, well, let's start with time, because this one I already made obvious. You have the time dimension, right? You want to have the data for every year, maybe even every quarter, every month, every week, you know, so you have the time dimension. Another dimension that is very common is the geographical dimension. You have the whole world with continents and countries and regions and cantons and Gemeinden and so on and so on. So this is also something that is typically covered in sales use cases. The C-level executives want to see the distribution over the world of their sales. If you are looking at sales data, you might also want to see the people and the teams of the salespeople who are selling, because you want to compare the performance of the teams, right? So this is yet another dimension that you can have. Then you can have the what dimension, which is so what means several things. So one of the way to see the what is servers, smartwatches, so categories of products. Another way of seeing what is what we call a measure. You might want to know about the quantity of products sold in Switzerland by a team in 2022. Or you might want to see the Umsatz, the revenues for Switzerland 2023 for a specific team. Or you want to see the profit, or you want to see in the balance sheet the assets, current assets, non-current assets, and so on, right? So this also is what we mean with what. Then you can have the currency. Maybe you have the data in US dollars, in euros, in rupees, and so on, right? So these are some of the dimensions, but there can be many, many, many others. You can have company segments, you can have scenarios, you can have many, 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 right? Who is with me? All right. So these are 5. I put 3 in there, but you really have to imagine that it can go beyond 3 or even 5. Now, if I had these 5, I don't know you, but as a human being, I have difficulty seeing more than 3 dimensions. With a bit of effort, you can kind of see 4, maybe 5. If you focus on hypercubes, I think some blind people are actually able to see 4 or 5 dimensions, which is very impressive. But most of us cannot do that because we are not used to this. We are only used to 3 dimensions. So what we do instead is that we take these little cells right here. Let me come back here. Imagine, so this is what our babies basically do. You take these cubes, you just collapse the whole thing on the floor, and then you pile them in a tower on top of each other, right? So imagine you do that. This is what you get. Here, I took the cells and I piled them up on top of each other. And on every layer, I have the value in my cell and where the cell was. So for example, that was a cell corresponding to Germany 2022 Peter, and with a value of 1,000. And here I see that I had 8 cells, and it was in a cube with 2 countries, 2 years, and 2 people. So that was basically a 2 by 2 by 2 cube. Who sees that? Right? 2 by 2 by 2, 8. 2 times 2 times 2 is 8. So I have 8 values. And when I do that, when I actually collapse the cube and pile the cells on top of each other like this is called a fact table. Fact table, remember that word, very important. This is a fact table. Do you see that when we do that, we are no longer constrained by the number of dimensions? I did it with 3, but if you want a 4th or a 5th or a 6th dimension, you just add columns, right? That you know how to do, to add columns. So that's how we solve the problem as humans, to visualize many dimensions with a fact table like this. In fact, when you use spreadsheet software to deal with data cubes, you can do it. Many Excel has it. I think probably LibreOffice, OpenOffice, they'll probably have equivalent functionality. It's called the pivot table. Who has ever used the pivot table functionality of the spreadsheet software? You never did it? I encourage you to try it out after the lecture in the exercises. What you need to do is basically import a file. Typically, so it's a CSV file. You might get one from the TA team that you take from the internet, or you can even just put the data yourself in the spreadsheet. But basically, this is what you need to have in your spreadsheet. Try to create that. You can copy paste that and put it in a spreadsheet. That would even probably work. And if you have it like this, you just select this right here, and you go to the menu and say pivot table. It's going to create another view somewhere else, and then you can start manipulating that in a way that I'm going to show you now. Right? So this is really something that's, you know, off the shelf. You can find it in spreadsheet software. So now I'm going to start formalizing things a little bit. So here it was just a special display, but if I want to formalize a little bit, this is a bit closer to reality, right? The same thing. So I really have the value that must be numbers in there. I had the dollar. So the dollar, I take it away and put it here in the currency axis. I told you this is one of the dimensions, but here it's all dollars. And then I add these square brackets, which is a way for me to know what we're talking about. So all of these here are basically members of some dimension, right? Peter is a member of the salesperson team. This is called an axis because we'll see later, that's why it's called pivot table. We can actually pivot around them. So my dimensions are called axis. So I have the location axis, the period axis, the salesperson axis, and the currency axis. And the members of my period axis are the year 2022 and the year 2021. And in my location, I have Germany and Switzerland. And again, I just put this square bracket member, just to remember that it's a member of a dimension right here. For whom does that make sense? All right, very good. Now, we can start doing fancy things with that. The first thing that we can do is called slicing. Slicing means that I look at my cube in my head, I visualized it as a cube. I want to extract a layer of the cube where a specific dimension has a specific value. For example, I want to extract specifically Switzerland. So again, visualize it here. Maybe this is Germany, this is Austria, this is France, and this is Switzerland. And I want to just take Switzerland out of my cube. That's what I did from here. I had Switzerland and Germany. Now I just take Switzerland. Who sees that this is kind of like a selection? You see that, right? I'll come back to that. This is kind of the way you map it to tables a bit later. So this is called slicing. So you can either visualize the slicing on the as a selection on the facts table, or even better in your mind, visualize it on the cube like this. Right? It's even more visual. Okay? And then what we start doing when we actually play with cubes like this, and this is exactly what Excel is going to do. If you actually activate the pivot table, it's going to create a view like that. When you slice, what you slice on will be nicely put at the top. It's called also a filter. So here, because I sliced on Switzerland, so instead of keeping Switzerland right here, I'm moving it over to the top here saying, okay, location is Switzerland. That means that it applies to everything here, right? I just specifically sliced on Switzerland. I did the same with USD because it was all USD anyway. So I just simplified and took it there. Okay, still with me? All right. But now something interesting is happening because I have two dimensions or two axes left. That's not really nice, is it, right? Because this is basically a 2x2 cube that we have left. There's 2020, 22, 21, and there's Peter and Mary, but I'm still listing them on top of each other. But what is a 2x2 cube? It's basically a grid, right? It's a table, it's something two-dimensional, it's flat, it's something I can actually see. And for this reason, I might as well do it. I can actually visualize it as a 2x2 cube. This is called cross-tabulating. When you do that, you basically, when you have two dimensions left in the what you want to display, then you put one of these dimensions on the rows, Peter and Mary, and another dimension on the columns, 21 and 22. These are called dicers. You dice on the salespersons and on the period, and these are called the slicers because you slice on Switzerland and US dollars. Who heard of slicing and dicing before? Who has heard this expression? Never? So you might hear it in the future. We call it slice and dice. When you have a data cube, you slice and dice. This is something that you might hear. And slicing and dicing means this. You slice by projecting to, no, I shouldn't use the word project, by filtering or selecting a specific value for some dimensions. And then you dice on two dimensions, and now you see it's very nicely displayed like this in this 2x2 grid. And that for a human being is wonderful. It's two dimensions. That everybody understands. You don't need to be a computer scientist, right? Very, very visual. Okay? So now I make it even fancier. Basically, these are the views, by the way, of that an accountant. I'll talk about XBRL later, but his name is Charles Hoffman, and he uses this convention, these visual conventions for dicing and slicing data cubes, right? So again, it's the same thing as here. I just drew it a bit nicely with my domain, my members here, and my domain and my member on the rows, and my 4 values in here, and my slicers in here. So now there are 2 dicers here, right? Because we have rows and we have columns. In practice, it's also okay to have 1 and it's also okay to have 3. Well, if you have 1, it's just more boring. If you have 1, you just have rows and that's it. Or you just have columns and that's it. It might be more common to have just rows, right? So if you have 1 dicer, that's it. You only have 1 column. How do you do 3 dicers? I guarantee you this is something you've seen. It's the tabs. You remember, in a spreadsheet, you have the tabs at the bottom. So if you have a 3rd dimension to dice on, and the first 2 are on the rows and the columns, you put the 3rd one on the tabs below. And then you click, in the UI, you click on the tabs to vary the value of the 3rd dimension, right? It's a bit less common, but you could use a 3rd dicer in the tabs. Okay. And so what you want to do when you open like this a pivot table or want to manipulate a data cubes, you look at all the dimensions that you have in your cube, and you just, for every dimension, you say if you dice or if you slice on it, right? Either you want to select a very specific value, or you want to put it on the rows or on the columns and vary it by value. Who is still with me? Right? Try to do it really intuitively. Okay. So now, let's go to the next level. One more thing that you can do. It's aggregation. Note that aggregation is not new to you. We've seen it with group by in SQL, right? So maybe you start connecting some dots. But basically, aggregating means that I'm kind of merging my cells along a specific axis. If you look carefully at what happened here, I merged it in depth. You see, I basically merge these 3 cells are merged like this. So I basically squeeze my cube like this, and I had here a 3-dimensional cube, and now I get a 2-dimensional square. What did I do? I basically aggregated the values that had, for example, the same country and the same time, for example, and I did a sum or an average or a max or a mean or whatever aggregation function, right? For whom does that make sense? All right, so let's do it with the data, with this. So imagine that I want to do my aggregation like this. So I put in colors what belongs together. So I basically would like to aggregate by, what did I aggregate on? By period and salesperson, right? I want to keep the period and salesperson, and I want to get rid of location. Location would be the dimension I basically aggregate. Let's do a sum. I basically want to have Germany plus Switzerland, right? But I still keep the distinction of the period and the distinction of the salesperson. How much am I going to get for 2022 Peter? For my sum is going to be 6,000, exactly. You see? That's what you get. Now, if I click, I will get exactly that. Yeah, 6,000. And you see where the other values come from. 8,000, that was basically 2 plus 6 here. You have Switzerland plus Germany. Then the blue part, so you have 3,000 plus the other side, 3,000 plus 7,000. That's again Switzerland plus Germany, this time for 2021 Peter. And then we have 4,000 plus 8,000. That would be for 2021 Mary, and Germany plus Switzerland. And these are exactly the values that I have in here. So you see, period and salespersons, they're still here. That would basically be my 2 dimensions in here, salesperson and year. And this here, the depth here, would be the country, right? But since I aggregated, that's no longer Germany of Switzerland. Let's say it's the whole world. Of course, you would do it with many more countries, but if it's the whole world, then I'm just putting world. And now it's just a convention, but you no longer say member, you say domain, because that's the whole domain of the location, the whole world, okay? And so then what you typically do in the views is that it's always the same here, it's always the same there, so you take them and put them all the way up here with the world and the USD, and now you have 2 dimensions left. Oh, 2 dimensions left, then automatic thought, slice and dice. I can put these 2 values like here. So you see what happens that's different with before is that now instead of a filter of just filtering on a value here, I aggregated over the whole world with a sum. And I have these 4 values. All of that you can do in spreadsheet software. Just put in a file that looks like this, put that in your spreadsheet, select it all, click on Activate Pivot Table, and then you just need to do some drag and drop. You need to drag and drop location over here, drag and drop currency over here. You need to click here and then say what you want. You need to drag and drop, sorry, on the rows, the salesperson axis, to drag and drop the domain axis. You can even sort, you know, and organize the order in which you want them, and so on and so on. Who is with me? Right? Okay. Then, what do we do next? What we love to do, and again, that's what the spreadsheet software is going to do for you, is the totals. Because we are interested in summing these things. So if I have now the sales by Peter and the sales by Mary, I might be interested in the sum. And so I typically do it on an additional row. I also have a sum over all times that I put on the right, and then the total, the grand total over there, right? That I'm sure you've already seen before, this way of doing things. Now something interesting is happening. This here has it's not a rectangle shape. It's called an L shape. It's strange when I do it like this. This is an L shape. Do you see the L? Basically, the domain here that contains my 2 members, there's kind of a hierarchy here, it aggregates in here, in that column like this. So typically, instead of saying total, you just merge the cells and put it in an L shape. Okay? So what that tells us, when I start seeing that Germany plus Switzerland gives me the world, or I have a grand total on salespeople, on times, and so on, what I start seeing here is basically a hierarchy in my dimensions. It's not just flat. It's not just a list of years or a list of people or a list of places. there's a hierarchy in here. I basically have a hierarchy. It's the easiest to see here. I have the whole world. Then below the world, I have the continents, Europe and Asia here. Then in Europe, you have the countries, Switzerland, Germany, and others. In Asia, you have India, China. In Switzerland, you might have Zurich, Geneva, Interlaken. If I directly put Gemeinde, you could have the cantons in between. But this is a hierarchy. That is very important, right? And that hierarchy, all at the top, has a whole domain. These are also hierarchies. They're even simpler, but you could even imagine having sub-teams right here. You could have a more complex hierarchy of the salespeople. But basically, Peter and Mary, and then the whole domain, that's basically everybody. And then all times, that's also a domain. And what is really cool is that in that case, it was the flat hierarchy with just some values and a total. But if you take the countries hierarchy, which is more than 2 levels, you have more levels here, then this is how you do it. And look at these L shapes in here. You see, you have Zurich, Geneva, Interlaken, and Switzerland is basically encompassing them. Then you have this nice L that basically gives you the aggregation. Berlin and Frankfurt, then Germany, and again, the nice L shape that gives you this. Then Europe that has Switzerland and Germany, that's one upper layer, again, the L shape. Then you have Delhi, India, Beijing, China, Asia, and so on, and then the whole world. For whom is that clear? Right? It's the power of the L shapes. But the L shapes, we only use them for the columns. We don't use them for the rows. For the rows, we do it more like this. And this is the boring counting statements that you find in the yearly reports of the companies, right? So basically use indentation in here, maybe some double lines, some bold, to just emphasize the subtotals and the totals, right? And this is exactly how financial statements are going to look like. So far, so good, right? Okay. So when you start doing this, we're going to have a break in 3 minutes, but I still have time for this. When you interactively manipulate that kind of data, one thing you might want is to get rid of the details. Maybe you're not interested in the individual cities. You're only interested in the countries and continents, but not the cities. You can remove them like this. No, like this. Like this, yeah. This is called roll-up. This is called a roll-up. You go from here to here. You just remove details. I can roll up again. Maybe you don't want the countries. There you go. Now you have the continents, or you can even roll it up completely all the way to aggregate over the whole world. And then typically you don't keep it, you just put it up there, right, as in the slices. By the way, this is an example where I have only one dicer left. I only dice on the salespersons, but I don't dice on the columns, right? There's only one column. Who sees that? Right? Awesome. That's the break then. Let's take a break. And after the break, I will show you how this can be implemented on top of a relational database and on top of SQL in order to get the data we want to put in our cross-tabulated view. So I'll see you in 15 minutes, 15 past 11.